Hello everyone, my name is Jordan Betancourt. I am the prototype development lead at ETHSign. Today I will be helping you understand how to interact with smart contracts on the Ethereum virtual machine. So let's get started. First off, what you will need is a network-specific RPC URL. This will help us communicate with the blockchain and with the smart contract that you are looking to use. So for example, you can get one of these links at Infura's website. So if you click on this link or go to this site, you'll be taken here. What you'll be able to see is a sample table here of what these URLs will look like. But most importantly, you will just need to create an account with Infura, and then you'll be able to generate an API key that will then give you a link like this. So you will need this in order to communicate with the blockchain, and this is just an easy way to generate one of these endpoints. Secondly, you will need a smart contract address for the smart contract that you are looking to use. In our case, we will be using this smart contract, which corresponds to a hackathon project that I recently helped build. Third, you will need a smart contract application binary interface. This is something that gets generated from the smart contract when it is being compiled using Hardhat or something else. And I can show you what this looks like here in a little bit. Lastly, you will need MetaMask or some other wallet provider to be able to interact with the smart contract on the blockchain. So a little bit about EVM, remote procedure calls. Whenever you're making a call to your smart contract, it is through a remote procedure call. The call structure is defined through your application binary interface, which I just described as being created by your Solidity code when it is compiled using Hardhat. It is important to ensure data is passed in the correct format, or you will receive errors that can be hard to understand. Sometimes these are responded back or sent back to you using binary or other very hard methods to decipher, and the hex values or other things can be extremely difficult for you to match up with your code base. So with that said, here's also another way to get the application binary interface. If you go onto Etherscan once your contract has been deployed, you scroll all the way down to the bottom when you're on this contract page. You will see that there is a contract ABI. You can copy this and use this inside of your code base. The other option is to get the JSON file that comes when you compile your code using Hardhat. So I have that right here. If you look in here, there's this ABI section, which if you look through it, is just a JSON object that defines the different functions, their call parameters, and other little structs and everything else, definitions that you will need to use when you're interacting with the blockchain. So if I come back over here, for instance, you can see that in this struct right here, we have this world ID external data. This is from the smart contract that was developed for the hackathon. So if I go back over here, I can search for this, and you will see that it is defined here with the types and the names. And so this is going to correspond exactly to what the block or the contract needs when you're sending data, sending a remote procedure call over to the blockchain. With that said, let's go ahead and get started. So our project to begin with is just a pretty simple petition website. It asks you to enter in a title here. You can provide it a message, and once you do this, you're able to add an image here. And our goal is to create this in the blockchain to start off with. So let's go ahead and do that. If I click create and share, it's not going to work right now because it's not connected to our smart contract. So first things first, how is this going to work? The first thing you're going to need to do is set up a provider. A provider is an abstraction of a connection to the Ethereum network. So this allows you to use that application ABI that you created when you compiled your smart contract. And from that, you are now able to have a connection to the Ethereum network using that RPC API that you have as well. So I come back over here. Let's go ahead and do that. We will be using the ethers.js library in order to complete this project. So what we're going to do is say const provider is equal to new ethers.json RPC provider. And inside of here, what we're going to do is pass in that pass in that RPC URL that you generated from Infura. So in my case, I have a function defined that takes in the library that I have, which is corresponding to the network that I have. So like I mentioned earlier, when you're on Infura, you can see that there are some different networks, and each of these are going to have a different chain ID, which corresponds to a different Ethereum blockchain. So if you're on mainnet, for instance, you will have one API key. And if you're on some other network, you will have a different URL here. Notice the naming here is different for each of these URLs. So in my case, if I go ahead and just follow this, you can see that what it does with this library, which is given to me by Web3 React, is that it has a chain ID, and we just have a basic switch case here that returns a URL depending on what network the user is using. So in my case, we will be using this. We'll be testing on base. If I come back over here, this is done. So now we have our provider. We still don't have a way to talk to the contract directly yet because it doesn't know what contract we want to use. So let's go ahead and do that. So we have a contract is a new contract. This is also given to us by ethers.js. Inside of here, you can see we need a target. This target is going to be that contract address that I showed in my PowerPoint a minute ago. So I come back over here and just copy this in. So now we have that there. The second thing it expects, as you can see in this little pop-up, is the ABI. So in my case, I will import this from the c3.json file. So I have c3abi.abi. So make sure that if you end up using that file, you directly link it to the ABI object. Otherwise, if you try and pass in just this file itself, it won't know, it'll consider it to be an invalid ABI because it's not in the format it expects. The third thing that you need to pass in here is your provider. Now this contract knows which blockchain to talk to. It knows what the format of the different functions and what it needs will look like, and it knows the specific address that you're trying to use. So this is good, but we still won't be able to make any write calls to the blockchain. And that's because at this point, we still don't have a user to pay for any of the gas fees or anything like that when we're making these smart contract calls. So now we'll go ahead and connect our current MetaMask user or the current user that is logged in, whether it's using Coinbase Wallet or Wallet Connect or something else. And once we connect that to this contract, we will be able to make write calls. So in our case, I'm going to go ahead and call this an instance. And this is going to be contract.connect. Then we have library get signer. And we are going to cast this as a contract. So this could all be done in just one line here as well. Once you create the new contract, you have the ability to connect your existing signer. This library.getSigner is a function that is defined by the provider that the user has that's logged in MetaMask. So all of this is coming from Web3 React, which is something that I already have set up in this project. Now that we have this instance, we're good to go. We now have our writable contract set up and ready to use for our function calls that are coming up next. So now we need to make sure that first off, we know what function we're wanting to call. In my case, I'm trying to call a function. I'll just go ahead and start typing this out. We are going to be using the instance object. And what we do inside of here is something called create petition. This function is given to me from the smart contract. So this is where it helps to have the smart contract either pulled up or at least some sort of documentation for what the smart contract is expecting. In my case, there are three things that it expects. It expects a hash, it also expects CID, and it expects some metadata. I already have this hash generated. In my case, I just create a random string and then I hash it using ethers.hashMessage. And that is something that's going to be a unique identifier within the way this contract is written. The second thing is a CID, which corresponds to some data CID storage. It's just an ID for something we uploaded to web3.storage. Third thing is a metadata object, which we are going to need to generate from this onSuccess data here that is given to us from WorldCoin's API here. So this is all going to be very specific to what you were trying to do. And for that reason, what I'm going to do here is just quickly copy and paste over a couple lines of code here that give us the data that we need. What we're doing here on this first line is actually given to us from WorldCoin directly. This is not something that is very common to do inside of any smart contract calls. But essentially what's happening here is this proof is an extremely large number, and it does not fit inside of just a regular number that can be stored on the blockchain or on the front end here using JavaScript. So what they end up doing is they split this into an array of 8 uint256 numbers. This is just specifically the format we are needing. Like I said, this is not common. This is just how it's handled. We are also going to be creating this metadata object, which takes in the root, which is just given to us here, the nullifier hash, which is also given to us here, and then the proof, which we just generated here. From that, you're pretty much done. This right here sets up what we need for the data to pass in. We already created the hash, we have the CID, we have the metadata, and this just looks like a normal function call. You have a contract instance, which is connected to your current signer through MetaMask or whoever wallet you're using, and then you'll just call the function that is on there and with the data it needs. I will say this though, when you are doing these kinds of function calls, like I mentioned with the error handling, this will throw errors if your contract reverts or has any other processing issues. So it is definitely recommended to do a try catch surrounding anything that you do on the blockchain. So go ahead and do a try catch here. What will happen with this error object, depending on the type of error, this may be an error object or it may be an error string. So typically what we end up doing is I have a store notification function here. All this does is it creates a little notification on the user's web page. And so this is going to be of type error. You could easily just console log this as well. But most importantly, you can do something like error.message and just see if that exists. If it does, then we'll print out error.message, or we will just print out the error object itself. And this is of type danger, which is good. But obviously I'm using TypeScript, it doesn't like that. So for the sake of time, we're just going to create an any type here. Now that we have that, we are good to go. What I will also do on my case is just to add in some additional UI functionality. I'm going to call another function here. And this way we can see that it succeeded on the front end. So pass in URL. This is fine for now. And then what we're going to have is the hash. And once again, this is just additional functionality that you would want to do on your front end if this is what you were looking for. This may or may not be what you're looking for. You may want something completely different. But in my case, this is just going to pop up a little modal with the share button that would have the URL and hash. In this case, for time, I'm just going to leave this as the letters URL instead of the actual sharing URL. So now that this is compiled, I'm going to go ahead and jump back over here to this. Come back here. I'm just going to refresh the page so we can start over. We're just going to call this petition and petition message just to make it simple. For this picture, I'm going to just, I guess we can do this. We can go ahead and have a little monkey, low resolution monkey. And yeah, this does not look very pretty, but it's still going to work. So we can go ahead and now we can click this create and share button. And by clicking this, the first thing that ends up happening is it's going to connect to WorldCoin, which is that ID kit thing that you saw there. And that was just the surrounding, here, I'll just jump back over here. Inside of WorldKit, that is this right here. So now that I click on that button, it has this little QR code for me to use. And I'm going to go over to my other window here. I currently have a little simulator open on their website. That way I can just paste in this QR code and verify myself. All right, and now it is verifying and success. Great. So now we have this verified. When I click this X here, it should have a MetaMask pop-up here asking me to confirm this call right here. I will confirm that. And now we can see that we successfully interacted with the blockchain. So now we have this URL / and then there's an ID here. And so what I'm going to do is just copy this. And now that I've copied it, I'm going to create go to a new tab, paste that there, and then I can go to localhost 3000 / petition and that ID, that ID there. In this case, it'll take it a second to actually load this data because of our indexing provider. So I'll come back to this here in a second for when we end up actually signing the petition. So with that said, like I just mentioned, it takes some time sometimes for the blockchain to update and for different indexing providers to even see those changes. So, you know, what if you wanted to, let's say, wait a little while before you actually did anything? So what you can do is, instead of just awaiting this instance.create petition, you can also go ahead and do .then, have a transaction. And on this transaction function, you can just do transaction.wait 1.then, and then you can do some processing here. So what this ends up doing is this waits for the transaction to complete, first off. And then once that transaction completes, it waits another period of time. In this case, it'll wait for another block on the blockchain to be processed, and then it will do something. So this allows you to, make sure that the transaction is confirmed, wait a little while, and then then from there you can do some processing in case things are more time sensitive. In our case, it doesn't really matter, so I'm just going to keep things simple. But as you can see, when I go back here, this could potentially be the issue if you try and read directly from the blockchain right after a transaction is performed. So I'm going to go ahead and save this file. So this file is good to go for now. The second thing that we are going to do is something fairly similar. When we go over to this petition, what I'm actually just going to do to save time is copy over this entire thing here, and we can just modify a few things to make sure it works on this side. So when we go into the petition file, obviously there are some things that are missing here, but in our case, that's actually pretty much it. If I just remove that, we still are going to need to have a provider. Provider is always going to be required. Contract is required. In our case, it's the same contract, same ABI, same provider we created earlier. The instance, same thing. Connect to your current library signer. The proof, same thing, given to us by WorldCoin. And the metadata, same format, same expected values inside of the smart contract. So the main difference here is now, instead of creating the petition, we are going to sign the petition. And also, instead of using this hash, we have a new thing that we need to do for our end. And this all comes down to data formatting. So I have some other helper functions already defined in this project. So what I need to do is get the bytes to a string. So we're going to take in just a uint8 array in JavaScript, turn that into a string, and that's going to be from a hex string. And that is going to be our petition ID, which is actually potentially null. So I'm just going to do this and take the substring of that from 2. So in our case, the petition ID starts off with 0x and then some, the actual value itself. What I'm doing with the substring is just going to take this value and use that. So we have that. the other option, like I mentioned, is that this could be an empty ID in case somebody uses the wrong URL. So for time's sake, it's just going to be a quick thing there to fix that. And this is actually all that we need to do to make this work. So we still need the same metadata. This is requirement for WorldCoin, which we are using to verify users' identities. And then this is going to just be the data that this signed petition expects and needs to process. So go ahead and save that. And now if I come back here, all right, so as you can see here, this petition loaded. We have the title we set, the message, and then in the end we also have this monkey, which I uploaded as the image for the petition. So now what we want to test out is the signing portion. So I'm going to go ahead and start this. So I'll go ahead and click sign. We see we have this QR code. Need to go ahead and input this into WorldCoin. And just as a reminder, this is not something that you normally need to do. This is just something that, this additional verification is a functionality that we used from the hackathon. So for the actual signing portion, that all takes place after this verification. So now that we're verified, I will click this X, and what you will see is a MetaMask pop-up. And this MetaMask pop-up is going to be our actual interaction with the smart contract that we just created. So I'm going to click confirm here. This is done. We're good to go. This also brings up a little share functionality here. That's actually not supposed to be there. So if I go back into our code, go over to petition, we can see that I ended up copying this show modal over, and I can just remove that. If we wanted to leave that in there for the sake of this project, we could, but at the end of the day, our goal was to get this signed, and that is something that we just completed. As far as this hackathon project is concerned, we did not take the time to immediately update this, even though we know this user just signed something. So this is something that we'll also need to wait another minute for, to let this indexing service that we have from the blockchain update and just read those latest blocks to add this signature on here. Once all of the signatures are completed, what this will look like, if I go over here to this other one which has previously been signed, I'm just going to refresh that because it looks like the image did not load. Not sure what's going on there, but at the end of the day, on the right hand side you can see we have some signatures listed. Since this was the hackathon project, you know, we have some discontinuities here with this one here, even though we have two signatures, but we do have these two signatures for this particular contract. And we can also see now that this is working. So essentially the idea here, once again, when we actually interact with the smart contract, is we need to create a provider so we can know what the remote procedure call endpoint is going to be. This is where our ethers.js contract is going to connect. And then with this provider, what we'll end up doing is creating a contract that links to that provider, just to that different RPC URL that we have. And we'll need to tell it the contract address and the particular binary interface for that application. From there, we need to create this instance, which is just the regular contract with the signer attached. This signer, once again, is just the particular account that we have logged in through MetaMask. So if I go back over here to this page, you can see that I am currently logged in. We can see my ENS alias here, and if I expand this down a little bit, I could copy my address or do other stuff that we have implemented here. So that's going to be what this signer is. From there, you need to set up the data in the correct format that your contract expects it. And in our case, that included this complicated little section of code here, which just splits a big number into a bunch of smaller numbers. That way the smart contract can properly read it. But in addition to that, you just pass in everything else kind of in a JSON format with, you know, root, and then this is what's expected, nullifier hash, this is what's expected, proof. And inside of this contract, you would be able to see that we are expecting in a string as the first parameter, and then a struct as the second parameter, where that struct is going to have a root, nullifier hash, and proof. And if any of this fails, we have a notification that will pop up on the screen. This notification is just going to print out the error message that we receive from the smart contract, similar to how you do a traditional just fetch call or something along those lines. And that is how you interact with a smart contract. If you wanted to just retrieve something from a smart contract, I have another little section of code here from a different project. For this project, I will not be running it, but I just wanted to take the time to show you how this looks if you want to get a result from the smart contract. So both of those two calls that we just programmed were both meant for writing to the smart contract. So they required us to have that instance with the signer attached. For read requests, you do not need the signer to be the person to be logged in. You do not need to connect the contract to a signer. So we're actually able to use the contract object directly. And when you do these types of calls, you just need to await the contract, the get, whatever it is, pass in the parameters just like you'd expect on a traditional function call. And then you can add this .catch afterward to catch the errors that happen here, and then you just do some sort of processing if that happens. It is important to note though that sometimes in certain instances there may be no catch thrown here, and your result could be something that's empty. So in this case, I have an additional if statement here to verify that this offer object we have retrieved from the smart contract is actually an object, or is not undefined, not null. And if that is the case, we just double check and make sure that the items returned for the application logic here are what we expect to see. So in this case, there are 3 different internal arrays inside of this object, and we just want to make sure that these are all non-zero. If that's the case, then we just return this offer object as our data. This is just the response type that we used for this different website. But at the end of the day, this is pretty similar. You could still use the instance here. It is totally fine to use an instance of a contract where there's a signer attached, but it's not needed. It's just additional information that is good for you to know, but not necessarily required for the sake of the program. With that said, this is how you read. Back over here, same thing for writing. And just as a reminder, you can attach a .then to this, which will return a transaction. And you can do transaction.wait a certain number of blocks, and then do some other additional processing here. And this is just going to be useful if you know that you want to make sure the network confirms this transaction. You want to make sure your application does not prematurely tell them everything is okay. But in the end, for what we are doing, it is perfectly fine to just write to the smart contract and move on. So with that said, I thank you for taking the time to watch this. If you have any questions, feel free to reach out to me. But that is how you interact with smart contracts. So thank you very much.